Hello, I'm Sachin from the Faculty of Electrical Engineering, Mathematics and Computer Science at Delft University of Technology. In this tutorial, we will learn how to implement the closed loop speed control of a DC motor. We will begin by briefly reviewing the inner current control loop and discuss how pole cancellation simplifies its dynamics. Then we will move on to the speed control loop, derive its discrete time equivalent, and finally implement the model on the ESP32 microcontroller. Let's start with the inner current control loop. The typical structure of the inner current control loop is shown here. The input is the reference current, and the loop ensures that the actual current follows this reference precisely. To simplify the model, several assumptions are made as shown in this slide. In the lecture, we discussed that by using pole cancellation, we can tune the PI controller parameters so that the closed loop transfer function becomes approximately equal to 1. This effectively means that the current loop behaves as an ideal inner subsystem, simplifying the design of the speed and position control loops. Now that we have reviewed the current loop, let's move on to the speed control of the motor. The speed control loop is shown in this slide. Here, the DC motor and its current loop form the inner system we just discussed. The speed controller acts on the difference between the reference speed and the measured speed to adjust the armature voltage accordingly. From a control theory perspective, the same loop can be represented more compactly as shown here. The PI controller, labeled CM, regulates the mechanical system GM. The open loop transfer function LS is shown in equation 2. We can also calculate the proportional loop gain as given in equation 3. Now let's see how we can obtain the discrete equivalent of this closed loop system. Because the resulting discrete equivalent is of higher order, calculating the coefficients manually can be quite challenging. Therefore, we use MATLAB or Octave to perform the discretization automatically. In MATLAB or Octave, the first two lines of code define the continuous time domain model for the closed loop system. Then, using the C2D function, we can obtain the discrete time equivalent with the chosen sampling time. The resulting numerator and denominator coefficients are stored in cell arrays, which can be easily accessed from the terminal using the commands shown at the bottom of the screen. Let's now discuss the implementation of the model in the ESP32 microcontroller. Once we have the coefficients, we can express the model as a difference equation. The one shown here is of fourth order, meaning it depends on the current and four past samples of both the input and the output. This is the equation that we will now implement on the ESP32 microcontroller. Let's open the Arduino IDE and take a look at the code. The implementation is quite similar to the one we developed in tutorial 5, with just a few small differences. First, the buffer size is higher to store all the past and present values. The coefficient corresponds to a sampling frequency of 100 Hz, which we determined during the MATLAB or Octave discretization. Thereafter, the difference equation is implemented in the ISR, and after the calculation of the new speed values, the calculated and reference values are stored for the next computation cycle. In this setup function, the ESP32's hardware timer is configured. The timer in this case runs at 10 kHz and the ISR is executed every 100th interrupt, resulting in a 100 Hz update rate for the motor model. The timer attach interrupt function links the timer to the ISR, and timer alarm specifies how often the ISR should trigger. Next, instead of sending voltage as the input reference, we send the speed reference directly to the controller. The speed reference toggles between 0 and 80 every 2 seconds. The microcontroller then calculates the corresponding control action based on the difference equation and updates the output accordingly. Let's now upload the code to the ESP32 and observe the results. After uploading, we can visualize the motor speed using the Better Serial Plotter tool. As we can see, unlike the sluggish response we observed in the open loop implementation, the closed loop speed control allows the motor to reach its reference speed quickly and accurately. Let's summarize what we have learned in this tutorial. We began by revisiting the inner current control loop and discussed how pole cancellation simplifies its dynamics. We then examined the speed control loop, derived its closed loop transfer function, and discretized the model using MATLAB or Octave. Finally, we implemented the resulting difference equation on the ESP32 microcontroller and observed a significant improvement in response performance. This concludes the tutorial. Thank you very much for your attention and good luck with the rest of your studies.